Hello and welcome to our project presentation on state sequences in primary visual cortex and secondary motor cortex population dynamics. For our project, we decided to work on the Steinmetz dataset, which provides spiking neural data across many brain regions that were recorded during a visual discrimination task. The overarching question we wanted to answer was whether we can infer behavior during the visual discrimination task from neural activity in the mouse cortex. And specifically, we wanted to investigate whether cortical activity unfolds as a sequence of discrete states, as has been found by several other studies before, and whether these states reflect behavior.
When starting, we explored the raw data and decided to study the secondary motor cortex and the primary visual cortex. This way, we can correlate neural activity to visual discrimination tasks and some behaviors like locomotion, which have been proven in earlier studies to have an effect in earlier visual areas. Later, we worked on implementing the hidden Markov model and fitting it to the experimental data. By comparing the states found by the hidden Markov model to the behavioral data, we were able to verify the implementation. In these neural recordings, you can see the behavioral time points starting from the stimulus onset to the feedback time. The first neural recording from V1 clearly shows at least two states, before stimulus onset and after. We also made the observation that these neurons were recorded from a monocular region as they respond only to right stimuli. In a neural recording from M2, the correlations to behavioral tasks are not as distinctive, but when looked carefully, higher firing rates can be seen in some parts.
But how do we quantify these states of neural activity? An ideally suited statistical model for this endeavor is a hidden Markov model. The basic idea behind that is that our observations, which are in this case the spiking activities of neurons, can be used to find hidden states, in our case firing rate vectors, which could represent lower dimensional representations of behavior.
So the first thing we tried was to fit a three-state model to the primary visual cortex data. And we found that for the 29 high-quality trials we've had, which included a high contrast level on the right side, the model seems to capture a lot of noise. Also, there seems to be no strong correlation between the behaviors and states. So the next step was to compare the findings to a set of simulated trials. And here we've simulated a number of trials using the actual firing rates found in the real data. And we found that fitting a three-state model to even 29 trials of simulated data works quite well. So the question that arose was that is it possible that we need either more experimental data to fit the three-state model well, or that discrete state sequences are not a good description of activity in the primary visual cortex, or that state sequences in the primary visual cortex represent more complex features. And the last thing we've tried using the primary visual cortex data was to fit a two-state model, which seems to capture both the onset of the visual stimulus as well as the task end, even though it's quite noisy. And besides the primary visual cortex, we've also looked at the secondary motor cortex, and we've tried fitting a three-state model to it, which seemed to correlate with behavior. And the first state is the baseline state, which occurs when there is no locomotion. The second state is a brief state right before the movement starts, which could represent movement initiation in the secondary motor cortex. And the third state is the state which occurs after the movement of the wheel starts, which we can see on the plot below and lasts until the movement of the wheel ends. And after the movement state, the model transitions back into the baseline state, which lasts until the end of the trial.
Finally, we would like to introduce ourselves. I am Asude Aydın. I obtained my bachelor's degree in electrical and electronics engineering at Middle East Technical University. This fall, I will be starting my master's studies at ETH and UZH Zurich in neural systems and computation, and my research interests include neuromorphic cognitive robots.
I'm Ivan Orsulic, and I'm a freshly graduated Master of Science in Information and Software Engineering from the University of Zagreb in Croatia. And some of research interests of mine are neuromorphic computing, spiking neural networks, and robotics.
And my name is Marcel Jüngling. I'm currently finishing my master's in biophysics at Goethe University Frankfurt and will be a PhD student at the Max Planck Institute for Brain Research starting this fall. And my interests include synaptic plasticity as well as neural network dynamics. And with this, we'd like to end and thank all of the people on the slide. Especially, we would like to thank Zana, who was an amazing TA, as well as Dr. Benjamin Scholl, who mentored us throughout the project work. Thank you.